the race to win wars and explore the stars have created some of the most fantastic products ever designed, and we use them every day, unaware of their amazing origins. On Wicked Inventions. The Barber wax jacket, a country classic with a World War II submarine warfare past. Teflon, the non-stick coating that helped develop the atomic bomb. 3D glasses, how 3D technology helped defeat Hitler. We reveal the amazing science and manufacture behind these wicked inventions. It is probably the ultimate in British countryside clothing, a jacket synonymous with shooting, fishing and horse riding, and yet just as at home on trendy city streets. But did you know this icon of country pursuits has an unusual link to providing clothing for submariners? It is the Barber wax jacket.
Wax jackets are particularly suited to the outside because they repel water, and it means that you and your clothing remain dry even in the most inclement weather. And in that way, people tend to rely on Barber jackets especially, but wax jackets more generally for protection from the elements. A really reliable piece of outdoor clothing.
The most recognisable piece of Barber clothing is arguably the B-Dale jacket. This design classic was introduced in 1980 and is still in production today, but its origins date back to 1894.
Barber itself started off life as a workwear brand in the late 19th century when it was founded in South Shields by John Barber to provide oilcloth workwear for everyday use. It became iconic when it introduced its thorn-proof wax, which was a technological innovation which helped its waterproofing, and then again in the 1930s when it was used by motorcyclists as an all-in-one suit for protection while riding their bikes.
The secret to Barber clothing's weatherproof qualities is the wax cotton that is used in its manufacture. From the late 18th century, sailors created weatherproof smocks by applying linseed oil to the coarse canvas that they were made from. Wax cotton was developed from this tradition, and in the late 1800s, an industrial method for its production was invented. The cotton was impregnated with a paraffin-based wax and then woven into a cloth. The wax repelled the water and so gave the cotton a waterproof finish. Barber's range of jackets and motorcycle apparel demonstrated the success of this hardy material, and with World War II looming, the Navy could see its potential.
In 1937, Captain George Phillips took command of the submarine HMS Ursula, and he was dissatisfied with the clothing that had been provided for his submariners. However, as it happened, one of his junior officers was a motorcyclist who owned a Barber all-in-one suit for motorcycling. Captain Phillips ordered that the officer in question be hosed down with a fire hose on deck to check the waterproof nature of the Barber suit, and being satisfied that it was much better than anything he had been given, he commissioned Barber to make a special two-piece suit in their waterproof cloth for use on his submarine.
And this became incredibly popular, and it became the most efficient and practical way for submariners to dress during the Second World War. And that's also the start of what we now recognise as the Barber jacket. It was really born in the beginnings of the Second World War.
Today, Barber continued the production of their jackets in their spiritual home of the South Shields in the northeast of England. The production of a Barber jacket begins in the cutting room. Rolls of fabrics for wax cotton jackets and linings in tartan, nylon and moleskin are brought into the cutting room. There are 3 tables. One cuts nylon and moleskin fabrics, another cuts check lining and cords, and the third table usually cuts thorn-proof wax cotton fabrics. At the end of the cutting tables, the rolls of fabric are ready to be cut. The fabric is rolled out onto the table, and a sheet of pink or white paper separates each new roll, ensuring there are no colour variations between orders. Computer-generated patterns that have been drawn to garment specifications are placed on top of the rolled fabric. These patterns are drawn in such a way that they make best use of space and therefore create as little wastage as possible. It can take up to 60 minutes to cut the patterns, bundle them together, and put them onto the factory prep lines. Each person cutting wears a chainmail glove to protect them from the very sharp blade. The cutting process is highly skilled work, and most of the people in the cutting room are long-serving members of staff and experts in the trade.
The garment process themselves is a way of taking different pieces, flat patterns, and wrapping it around a three-dimensional shape, which is your body. When you make a jacket through a production unit, you break it all down. You take it all to bits, a bit like a car starts off with a chassis, it has its wings and wing mirrors. A jacket is no different. It has a lining, which is the inner, and it has an outer. An outer has pockets, and the inner has pockets. And you build up slowly. You do all the small bits first, you make the pockets, and then you attach them to the front. You make the back with any features like vents, etc. And then you attach the front to the back. And then you attach the sleeves and you attach the collar. It can all be broken down into a systematic process, and then the garment is assembled slowly till it starts off from flat fabric and ends up as a three-dimensional object.
The newly cut fabric is moved to the prep area, where all the preparation work is carried out on the fabric in order to ready it for the production line. The team leaders take the cut fabric and pass it on to the relevant machinist. Tasks carried out by the prep line include jacket belts being produced, various pockets being made and attached to the lining, lab stitching, amongst other detailing, and also the stitching together of the left and right side of the front, and back linings being stitched together. Once all this has been completed, it is time to move the fabric onto the main production line. There are 5 production lines in the factory, and each can make different styles of garment. The production line can manufacture up to 50 styles of wax jackets in total. Each machinist takes a garment piece from the rack, completes it, and moves it on to the next member in the sewing line. There are many parts that make up a Barber jacket. The Beadle jacket being made here has a total of 160 different parts. This factory produces a new garment every 3 minutes, with 36 people lending their hands to make one jacket from start to finish. They are capable of producing 3,000 jackets per week and a whopping 130,000 per year.
As well as dealing with all the different details on the jacket, there's a significant factor to the jackets in that, because they're mainly men's jackets, mainly big jackets, by the time the jackets come off the line, they are a significant weight. And I'm full of admiration of our skilled machinists who can not only stitch these garments in a way that is robust and can be repaired, but then they can handle these jackets, which are really quite heavy, and they handle them in a nimble way, in a way that retains the crispness and precision of the manufacturing.
Now that the jackets are almost complete, they are moved on to the finishing stage of production. The garments are first marked with China marking pens. These markings show where each stud should be placed. Once marked up, they are moved to the studding machine. The jacket is lined up in the machine via infrared light, and the stud is attached. Now that the studs are all in place, the jacket is checked for the final time, and once the jacket has passed its final visual check, it is ticketed with all its relevant labels and backed up, ready to protect its new owner from almost anything Mother Nature throws its way. Now that is a wicked invention. Cooking pots coated with this super slippery substance mean that even the worst cooks can't get burnt food stuck to their frying pans. It is also used as waterproof material and played a vital part in the development of the atom bomb that ended World War II, and its name, Teflon. PTFE, or polytetrafluoroethylene to give it its proper chemical name, or as we like to call it, Teflon, is often mistakenly believed to have been invented in the 1960s by NASA. It was actually discovered by the American chemist Roy Plunkett as he tried to find a non-toxic replacement for the gases used in fridges for the American company DuPont way back in 1938.
Teflon was actually quite an accidental discovery. The scientists at DuPont who were looking into tetrafluoroethene, and they had a big cylinder of it that they'd kept cold, and after a while they just were going to look at it and use it. And the problem they had was they opened the cylinder, tried to get the gas out, and nothing came out. And then they weighed the cylinder and said, this has the right amount of stuff, but we don't actually have any pressure from it. This is weird. Now, violating all normal health and safety laws that we have nowadays, they took the cylinder, cut it open to try to work out what was going on inside. And at the bottom, they found a white, waxy substance that was polytetrafluoroethene.
This fantastic new substance was found to be extremely slippery, non-corrosive, chemically stable, and possessed an extremely high melting point. Plunkett discovered it had been created due to the tetrafluoroethylene gas coming into contact with the iron from a slightly rusty valve, which had acted as a catalyst and resulted in the creation of the waxy polytetrafluoroethylene resin found at the bottom of the cylinder. The patent for PTFE was registered in 1941, and before coating non-stick pans was actually used as an important part of the American Manhattan Project to create the atomic bombs that would end World War II.
Teflon was used in making the nuclear bomb because what you needed to do was separate out the types of uranium from the radioactive one which you wanted to use for the bomb and the non-radioactive systems. And in order to do that, you have to process uranium as a gas in uranium hexafluoride. And the problem with uranium hexafluoride is it's very reactive. If you coat the walls of all the systems you're using to do the separation with Teflon, then you don't have that reacting and produce reactive substances. You can just transport the gas as you need to and then process it later to make the material for the bomb.
After the war-ending bombing of the Japanese cities of Hiroshima and Nagasaki, DuPont trademarked PTFE as Teflon, but it would be another chance discovery that would lead to the creation of the Teflon-coated non-stick pan.
A French engineer who'd worked for DuPont had brought some of this Teflon because you can kind of spread it on things, and he'd actually taken it and put it on his fishing rod, and he'd found that when he put it on his fishing rod, the tackle, the bait, it didn't snag, it didn't get caught up. And his wife thought this was quite amazing, and she said, why don't you apply it to a pan? So he brushed her pans with the Teflon, and lo and behold, you had the non-stick pan, which was a great alleviation to millions of housewives and cooks across the world.
And that French engineer, Marc Gregoire, would go on to create the Tefal non-stick saucepans that, from 1956, started saving cooks' blushes the world over. We may simply call Teflon-coated pans non-stick, but PTFE's slippery ability is actually down to a few different scientific reasons. To begin, Teflon molecules are comprised of carbon and fluorine atoms that are so tightly bonded that additional molecules from other substances, for example food, cannot react even when heated and bond or stick to the Teflon. Another contributing factor to Teflon's slippiness, the weakness of the van der Waals forces inside it. Van der Waals are adhesive forces that create friction between two substances and can be imagined as lots of tiny claws trying to grip materials together. The difference in adhesive strength between the materials can be demonstrated using water. As a water droplet falls down a piece of glass, it is hesitant and leaves a residue as the adhesive forces of water and glass act upon it. If a droplet of water is moved around a non-stick pan, the adhesive force of the Teflon is so weak that the weight of the droplet pulls itself easily across the surface, leaving a dry path in its wake. In addition to Teflon's non-stick low-friction properties, its high resistance to heat led NASA to use it extensively during the 1960s for coating everything from spacesuits to electrical wires, and even re-entry heat shields that probably led to the myth that they had invented the wonder coating themselves. Today, Teflon's use has moved far away from just the non-stick pan.
So you can use it in clothing. You can basically make a waterproof coat by spinning Teflon fibers with everything else. You can make umbrellas that are coated with Teflon so the water just rolls right off it. It's also used sometimes to wax the bottom of snowboards and skis so you can travel a little bit further and a little bit faster down the slope.
Teflon is used everywhere throughout the globe, from making the perfect pancake to coating the roof of the Millennium Dome. But its role in creating the atomic bomb means it is truly a wicked invention. Teflon is one of the few substances known to man that is so slippy even insects cannot get a grip on it. Another of its properties is that it is hydrophobic, which literally means it repels water. In nature, this can be seen on hydrophobic plants. Water droplets will form balls and just run off these plants' leaves. This is because the leaves are made up of hydrophobic molecules, meaning that they simply cannot dissolve in water. Our intrepid tester wants to put this hydrophobic effect to the test. For this experiment, you will need 2 pieces of tissue paper, a shiny piece of Perspex, super hydrophobic spray, and water, which is blue. Why is it always blue? Now everything's set, let's do something with that super hydrophobic spray. The intrepid tester takes one of the pieces of tissue and places it in his extra special spraying booth, otherwise known as a cardboard box, and covers the tissue entirely in the hydrophobic spray. So now we have an untreated piece of tissue on our left, and on the right we have our specially sprayed, newly created super hydrophobic tissue. How are they going to react with the water? Let's find out. our tester first pours a small amount of water onto the untreated tissue, and it instantly absorbs. What a mess. But what happens with the treated tissue? You guessed it, that tissue just will not absorb the water. That's real-life hydrophobic action right there before your very eyes. Just like those hydrophobic leaves in nature, the hydrophobic molecules in the spray are non-polar, meaning they do not carry a charge between their atoms. Because of this, there is no way in which the atoms can interact with the negative polar charge between the atoms in the water. Never quite satisfied, our very thorough tester has another experiment up his sleeve, this time with that perspex. He takes some duct tape and covers up a square in the centre of the perspex. He then takes the amazing super hydrophobic spray back to his special booth and covers the perspex in it. Back in the lab, our tester peels away the duct tape, revealing a square in the centre that hasn't been treated with the spray. He then takes his trusty blue water and pours it onto the untreated section of the perspex. Would you look at that? The hydrophobic area around the centre repels the water, effectively holding it in place in a nice neat square in the middle. So hydrophobic effects. Very impressive. This technology has redefined the cinema experience, presenting filmmakers with a third dimension of storytelling possibilities. But the science behind this amazing innovation is actually over 100 years old and was used by the Allies to combat the threat of Hitler's V1 and V2 long-range weapons in World War II. It is 3D.
3D has become a really popular way of looking at films, especially. Things come at you, explosions seem to be happening right in front of your face. You feel like you can almost reach out and touch what's on the film, and it really makes you feel like you're there.
Today, the term 3D has been used to describe a variety of techniques and technologies that essentially take a flat, two-dimensional image and convert it into a three-dimensional one, where a viewer can perceive depth to objects in the scene. The three-dimensional journey actually started with stereoscopic images, which came to public attention in the 1850s.
They were developed with stereoscopic glasses, that's how they were originally known, rather than three-dimensional. Stereo meanings two, scopic meanings seeing, so two eyes to see, which is how we see ordinarily. It was invented in 1844 and became popularised during the Great Exhibition when a 3D picture of Queen Victoria was taken. And what it involved was you take two pictures side by side, taking those, and then using special viewers which allow you to each eye to see just one image, allows you to process, as your eye does, one image and then another and combine them to form a 3D image.
In World War II, this novel technique was used for a serious and potentially war-winning purpose.
In 1940, pilots started flying over German territory in Spitfires, taking stereoscopic photographs of the terrain, and this meant that when the British military then looked at these images taken from the air, they could see really well not only the German landscape, but also the height of buildings and the kinds of buildings and structures that they were flying over.
Arguably their biggest success during the war was the work undertaken during Operation Crossbow, when Hitler's V1 and V2 long-range flying bombs and rockets were targeted. To aid their research, suspicious sites would be identified, and then a new reconnaissance flight would be undertaken to carefully take more detailed photos of the area. The pilots were instructed to take images on exact coordinates so their photos could overlap and the interpreters could build up a 3D view of the landscape using the same stereographic techniques employed for fun before the war. Undoubtedly, stereography played its part in lessening the impact of Hitler's terror weapons, and after the war, peacetime was the perfect place for a bit of 3D fun. The classic image of someone watching a movie or looking at a 3D comic book is that of the viewer, wearing a pair of cardboard glasses with a red and cyan filter over each eye respectively. This technique, known as Anaglyph, achieved popularity because of its simplicity and ease of use. These reasons were why NASA used Anaglyph technology on their probes to send 3D images back to Earth.
The red and blue filters, or the red and green filters, means that each eye only sees one image overlaid on top of a black background, which is designed to show the outlines of what you're looking at. This means that your eye sees two different images that have two different, subtly different shapes, and thus your eye starts to look at them and can reconcile them into a 3D image.
From a fun fad to war-winning reconnaissance and on to NASA exploration, stereography has been capturing our imagination for over 100 years. Today, Anaglyph glasses are still made by American Paper Optics from their factory in Bartlett, Tennessee.
American Paper Optics is a 25-year-old company. We've got 40 employees. We manufacture all of our own paper 3D glasses in our own plant. And our 25-year history we have sold over 2 billion 3D glasses. So basically you can figure that I've put glasses on about a fourth of everybody in the world.
American Paper Optics receive orders for a vast array of styles of 3D glasses. Each client can have their glasses designed specifically for them, so the first step in the production process of the glasses is art design and graphics. Once the designs have been finalised, the glasses begin life as huge printed sheets of card that are produced off-site. The sheets of printed card are then moved into a die-cutting press machine. The printed sheets are die-cut one at a time in a flatbed press. On the first pass through the press, the eye holes for the glasses are cut and knocked out. These eye holes have to be precision cut because of the next phase, which is the gluing of the film to the paper. In addition, the back of the glasses have to be perfectly aligned with the front. Now that the sheets have been eye-holed, they are ready for the laminating process. This is where the glasses are fitted with their all-important coloured film, ready to create the 3D effect. The first step of the process is gluing the film to the front sheet of the glasses, covering the eye holes. Once completed, the sheet is automatically folded over and the back is glued to the front in order to trap the film between both sheets. The glasses are inspected for quality throughout this process.
The real key to manufacturing a pair of paper glasses is really the gluing of the lens technology. So with our automatic gluing equipment, one of our machines can actually glue 50,000 glasses an hour.
This company didn't just produce glasses with 3D lenses though. They've branched out to reach a whole range of markets and customer demand.
What makes our product unique is the high quality printing, the high quality paper and die cutting and assembly that my staff does. But what really makes American Paper Optics unique is our lenses. We've got specialty optics that nobody else in the world has. Glasses that are used to demonstrate everything from eye diseases to 3D effects to amazing effects that allow you to even look at the sun during a solar eclipse.
After waiting for the glue to dry, the freshly laminated sheets are sent back to the die cutting machine again. It is at this point that the glasses are cut into their final shape. As well as this, they're scored in order for the glasses to be able to be folded.
What we're known for at American Paper Optics is our speed. You could actually call us on a Monday and get 1,000 glasses, let's say branded for your wedding, and we would have those glasses the next day for you, branded and ready to ship.
The sheets are then counted into stacks of 50. The glasses are then stripped from the sheets in stacks, noses pulled out, rubber banded and packaged into cases ready to be shipped. In some cases, customers request that the glasses come folded. American Paper Optics have a custom-built folding machine that can quickly fold bundles of 50 glasses, ready to be packaged. So there you have it, a dash through the hidden history, super science and amazing manufacture of products that you use every day, but have never realised their amazing background. The Barber wax jacket, Teflon and 3D glasses, all wicked inventions.